On wave phenomena. We're going to look at 4 wave phenomena that all waves have. So if you are a wave, or if something is a wave, it must have reflection, refraction, diffraction, and interference. And the goal today is for you to know what all of these things are. And we're going to start off with wave reflection. And so wave reflection is going from one medium, and so in this case, this could be air, into another medium. And well, not into because it's reflected off of it, but going from one medium to another medium. So this could be like glass. And you have a reflection. If the reflection's off a flexible boundary, and a flexible boundary, as you can tell, is one that can move, that flexible boundary will go up, it'll come back down, and the waves can be returned on the same side, which you'll see on the next slide. But let me go ahead and just cover what's on this slide. Incidence wave, wherever the wave starts, is called the incident wave or incident ray. And then when it's reflected after the reflection, it's called a reflected ray. And then between these two different medium, this is going to just be the boundary. And so this whole thing right here is a boundary. And usually there's some sort of interaction, something that will occur at that boundary. In this case, you see the reflection. So on a flexible boundary, the one that can move, you notice it goes back up, comes back down, and the wave is returned on the same side. So the wave returns, we'll call that upright because it's facing up that way and it's facing up again on the way back. Off of a fixed boundary, notice what happens here. So the fixed boundary is not allowed to move. And think back to Newton's third law. Where there's a force, there's an equal and opposite force. So when this wave pulls up on the wall pushes down on the wave. And the result of that is that the wave gets returned inverted. And so since it starts this way upwards, and it returns this way downwards, we call that inverted. So here are a couple questions. I'll give you a few moments to answer these. What kind of boundary is free to move, flexible or fixed? How does a wave return off of a flexible boundary, upright or inverted? And how does a wave return off a fixed boundary, upright or inverted? And so I'm going to keep on going, but you should pause video as you get to these parts if you're watching the video. And I'm not going to give you the answers because the answers are in the pictures, the animations right here, but they're also in the previous information that we just covered. Okay, so the law of reflection is a pretty straightforward one. When you have an incident ray, which is a ray coming in and it bounces off of that boundary, the separation between medium, it's going to bounce off of this thing, and we're going to call this invisible line that we're going to kind of measure from the normal line. So it's going to bounce, and we're going to compare the way the incidence ray should be compared to the reflected ray here. And whatever this one ends up being, so if this ends up being 25 degrees, this is also going to end up being 25 degrees, like that angle right there. Always from the normal, so the reflection, the incident coming in ray to the normal, it should be equal to the ray, the angle from the normal line to the reflected ray coming out. So if this was 40 degrees, this would have to be 40 degrees as well. Some harder questions might ask you, like, what would this angle be? But I'm not going to do it in this video. So if that was the case, then that might be something other than 40 because it's not part of the definition. Definition is always relative to the normal line here. And you'll see in the future, angle I will count for angle of incidence, and angle R in this case is the angle of reflection. We're going to use this angle R symbol for something later on in a future lesson when we get to refraction as well. So here's your question. If the incident ray hits the medium right here at 25 degrees, what is this reflection? What is the reflected ray going to go at versus the normal? Now, the next type of phenomenon, this is not reflection anymore. Now, and in fact, reflection would occur. You would have reflection coming back, but there's another principle when you're going from one medium to another. So let's go ahead and say this is air and this is water. Doesn't matter, it could be any two mediums. But when you have that boundary, we're going to just ignore, pretend like this doesn't happen, but it does happen. It both would happen. The refracted ray is going to be the ray that goes into the new medium. And what happens is you get into new medium from air to water. Well, air is faster and water is slower. So the ray is actually going to slow down. And when the ray slows down, there's going to be a bending that would occur. And so we're gonna have, once again, we'll deal with this mathematically later on, but we call this angle R for angle of refraction this time, because here we have a refraction as the light goes through, or the wave goes through into the new medium. And the changing of the speed is what causes the bending. And so if we have a change of speed, when we're going from faster to slower, the actual refracted ray is going to bend inwards. So normally this should go straight ahead, but since it slows down, it's going to bend inwards. And so we have the refracted ray coming over here, and it bends towards the normal line. So faster to slower towards the normal line. And then slower to faster, we're going to have kind of the opposite occur. So rays coming in, instant ray, hits that boundary, and right at that boundary, it speeds up. When it speeds up, it takes this angle in an outward direction away from this normal line right here. So slower to faster is going to be away from the normal line. So here are two questions asking you that. Person shines a flashlight off a pond and sees some light go through and some reflected back up off the pond. The ray started at the source before hitting the new medium is considered the what? And so you have the answers in this animation. Also, you can go back. Person shines a flashlight off a pond and sees light go through and some reflected back up off the pond. The ray after hitting the new medium that goes through it, so the one that's going through it into the new medium, what is that one called? And here we have a question. If a ray of light was traveling from air to water at a 30-degree angle of incidence, so if this was 30 degrees, would this angle right here in the slower medium be less, closer to the normal line, or more away from the normal line, or just straight ahead? And so that's what this question's asking you. Next question. Is this diagram correct? And if not, how should it be fixed? So take a look at faster and slower, and should it bend towards your way, and then answer this question. Is it correct? Or what should be the right answer? If you are doing my e-class quiz to go with this, just note that there will be some questions that are rearranged. So don't just look at A, B, and C here, and make sure you're looking at your actual answers. Okay, light is light bending towards or away from the normal line on the air side when you look at a fish in water where light travels slower? Okay, so we're talking about on the air side. Would it be towards or away from the normal line? So you can see where in reality this fish would be and where it actually is. And we draw a normal line right here. We take a look. It looks to the person like it's straight ahead, but is it towards the normal line or away from the normal line in reality? Okay, a person shines a flashlight off a pond and sees some light go through and some reflected back on the pond. The ray after hitting the new medium that bounces back without going through is considered the what? This one right here. What would that be? Which are these three words? Next phenomena that we have is wave diffraction. And wave diffraction is a bending that occurs not in a new medium. You're still in the same medium. So a wave is being created here, but as it goes around the corner, it has a bending around that corner at that spot. And so if it was just matter, the wave would go straight ahead. But someone over here can actually hear another person if they were speaking over here because of this bending, because of this diffraction that occurs. This is bending around a corner. So answer the question. Diffraction is the what? Okay, so next thing is going to be what we call superpositioning often, but we also more commonly call it interference, because we could call either the type of interference constructive or destructive interference. And the reason why we can have interference is because waves are not matter, they're disturbances of matter. And so they're actually energies, and energies can go through each other. And when they go through each other, they can either add or subtract. And so we're going to look at the different two. And the amplitudes are going to change when there's that interference during that moment that they're together. Destructive interference occurs like this. As you notice, the two waves are coming together. They subtract their amplitudes just temporarily. The waves as they go through, they pass each other. So notice how this one passes, and it still stays on the bottom, and this one on the top passes the other one, still stays on the top. It's almost like they never really interacted altogether. It's just their energies interacted temporarily, the disturbance interacted temporarily, and you saw the destructive interference as the amplitudes decreased. If it was complete destructive interference, that's where we would have just a straight flat line if you had two equal amplitudes, two equal energies passing each other, each on opposite sides, you'd have nothing going on in the middle for a second until they kind of reappeared after the interaction that occurred. So here's your question. Why can two mechanical waves travel through each other and not collide? Here's another question. With this one, we have the before situation, the during, you see the wave disappear. After, they pass each other up. Which one of these interferences would you have? Next question, you have the two waves coming towards each other, and during they add to each other, and after they pass each other up. Which one of these would you have? Just a note, conjunctive is not a word here. You're picking between constructive and destructive. Okay, and then now when we have waves created in water and ripple tanks, we can see these areas of interaction where there's constructive and destructive interference. And there's going to be areas where it appears like if you take a look right here, it looks like there's less going on, like right there in the middle between these spots. Well, that's going to be a nodal line where there looks like there's no wave because there's destructive interference. So the nodes where there's no wave, the destruction is going on. And then you have areas, so like for example, so you can see it right here where you have the maximum right in the middle. So you have these nodes right there, and you have this antinode in the middle. The antinode right there, the maximum, that's going to be where there's complete constructive or where there's constructive interference going on. So nodes, think of nothing. Now there's an experiment. So what light, like waves in the water are waves, but light's also a wave. And there's a double slit experiment that is often done in physics where you shine a single beam through of laser light through two slits very close together. And what you would expect to see if this was particles, like if you were throwing baseballs through these holes, you'd expect to see those baseballs all land in two spots, right here and right there. And that's what you would expect to see. You'd expect to see a banding pattern that would just look like this and this, and not what you see in reality. What you're going to see is a bunch of interference, more interference in a certain spot and less and less and less, but you see a pattern, not of two spots, but of many spots, depending on how close or how far the slits are. Different types of banding patterns will occur. So there's a video you can watch if you just type into YouTube double slit experiment. You'll have a bunch of different options. If you're in my class, you'll see a link to some accessory videos you can watch when you're done with this quiz. Next thing we have to get into, and this would be usually this will occur off of some sort of fixed boundary, but when you have a wave, and I'm going to draw it to the side because it might be easier to see. When you send a wave and it hits a fixed boundary, when it hits that fixed boundary, it's sent. Let's see if I can do this. I'm going to do the wave a little bit better. Okay, so when it hits that fixed boundary, one that's not allowed to move, it's sent and returned backwards. And it's sent and returned backwards inverted. And when it's sent and hit backwards inverted, and I didn't do this, these three waves should look about the same amplitude, not like they look. But when it's sent back, what's going to happen over and over, if you keep on sending that wave, and it keeps on getting sent back, what's going to occur is you're going to see this pattern. It looks like there's areas where there's nothing, or nodes. And there's going to look like there's areas, so right here you have three areas where there's antinodes. For spelling job. In the nodes, these side things count. And so you can count how many nodes and how many antinodes. And in this picture, this would have three antinodes where there's constructive interference and three nodes where there's destructive interference. Just in case you see this in a question, often they'll draw this to represent that the waves are kind of coming through. They're bouncing, they're going back and forth. These waves just look like they're standing there. They just look like they're in one place where the antinodes are, and then there's going to look like there's no wave where there's nodes because of destructive interference. Now, for this to occur, this wave has to be the same. It has to have the same frequency, same wavelength, same amplitude, and also it has to be, it has to be in phase with the other one coming back like that, so that you see what you see here. If you had a higher frequency, if I started vibrating this more and more and more, over time, you'd go from a standing wave that might be like this. And if I kept on vibrating a string that was stuck to a wall, at some point in time, you'd get to the next level of frequency. I probably passed it up. Yeah, I did a bad job here. But in general, you would actually go from 3 to 4 to 5. I went way beyond that. But as you just kept it on vibrating the string more and more and more, you'd see the standing wave disappear, and then you'd see the next level of standing wave with one extra antinode appearing in the center. But here I'm just getting at the higher the frequency, the more waves you have, the smaller the wavelengths. And therefore, opposite, the lower the frequencies, the bigger the wavelengths. So here's a standing node or standing wave with 5 nodes, 1, 2, 3, 4, 5, and then 4 antinodes. It's always going to have one more node than antinode. So that gets you to this question. What's the term for the reflection off a fixed point with the same frequency, wavelength, and amplitude interfering? Some points appear fixed, where others appear to be fixed at no amplitude, while others appear to be at maximum amplitude. So when I say fixed, it looks like these parts aren't moving at all, whereas these parts look like they're maximum amplitudes right here. And then how many nodes and antinodes does the standing wave that you see here have? And the ends do matter. So when you're thinking of the term node versus antinode, these things are going to matter. So you have the lines represent one of those things. I'm not going to tell you. You can rewind the video. That's if you need the help. And then these dots represent something else. So what is your answer? Next thing I want to get at is resonance. This is just a special property, especially when it comes down to sound. We'll hit sound a little bit later, and we'll talk about it then. But when you have a string that's going to start vibrating, you often, if you hit the natural frequency of another object, for example, the sounding board, which is the guitar itself, if you hit the natural frequency of that, what's going to happen is that everything starts vibrating and you have this amplification of sound. And if you knock on anything around you, that noise that you hear is the actual natural frequency. And if you can play a note at that octave, with that frequency, I guess you have different octaves, but if you play that frequency, it will start amplifying. It will start amplifying into the other object. And so people have been known to break a wine glass or something of that sort that might be a little bit thinner. If you tap on that wine glass, you're going to hear a frequency. And if you can amplify, if you can make a sound that's loud, powerful enough at the same frequency as the natural frequency of that glass, you can create that glass, you can cause that glass to break. But less aggressive, you're just playing a musical instrument. It's meant to do the same thing. You have the sounding board off the guitar that's meant to mimic the natural frequency, or the string, when you play it right, will vibrate at the natural frequency of the sounding board, and it'll just sound a lot louder and nicer. Another thing when we hear sound is the higher or lower you hear something, what you actually perceive, what a person hears. So that's my person, that's his ear. What's actually heard and translated in this person's brain is going to be the pitch. So when you hear something, you hear pitch, but it's all related to the frequency. Higher frequency, higher pitch, lower frequency, lower pitch. Force vibration, this is another term here. Force vibration, when you actually take this strum and you strum this note right here, well, you force the vibration into the string, but as a result of that string vibrating, you didn't actually vibrate the guitar, but the vibrate will be sympathetic. As a result of something that happened to you, or you did, something else also feels it, or as an effect from it. So here's your question. What's the dramatic increase of the amplitude of a wave when the frequency of applied force matches the natural frequency of the object? And then, to finish off the class, let's go ahead and just throw it together and answer these 4 questions. What property of a wave is described as a bending when passing through into a new medium? What property of wave is described as a bending outwards when passing the side or corner of a new medium? What property of wave is described as bouncing back off of a new medium? And then lastly, what property of wave is described as an interaction that occurs when 2 waves cross each other's paths? And once you answer that, then if you're in my class, I have a few videos you can watch that will show you breaking glass due to resonance. And then you have uh, another guy playing guitar, so using the sounding board, using that resonance. A couple other videos. There's 3 videos in total. The double slit experiment with Michikako, going through that's pretty interesting. So watch those if you have time still in the class period. If this is not a live lesson where I'm kind of walking you through it. Have a great day. See ya. And these are the 3 things.